The morning of March 19th, 1945, began like any other at the Yokosuka Naval Air Technical Arsenal, 25 miles south of Tokyo. Commander Minoru Genda walked past rows of captured American aircraft, his leather boots echoing against the concrete floor of Hangar 7. The air smelled of engine oil and salt from nearby Tokyo Bay. But today, something was different. Sitting in the center of the hangar, still wearing its faded navy blue paint and the white star insignia of the United States, was a Grumman F6F Hellcat, Bureau number 58312. It had been forced down 3 weeks earlier near Iwo Jima, its pilot rescued by American forces before Japanese troops could reach the crash site. The aircraft itself, however, had been salvaged largely intact. Now it belonged to the Koku Gijutsu Sho, the Naval Air Technical Arsenal, where Japan's best engineers attempted to understand why they were losing the air war so catastrophically. Genda approached the aircraft slowly. He had seen Hellcats before, of course. Every Japanese naval aviator who survived past 1943 had seen them. They had replaced the inadequate Wildcats and turned the Pacific Air War into a slaughter. But he had never been this close to one on the ground, never had the opportunity to examine the machine that had helped decimate Japan's Naval Aviation Corps. The Hellcat sat there, silent and imposing, like a predator even in captivity. What Commander Genda and his team would discover over the following weeks would not be a single revelation, but rather a systematic dismantling of everything Japanese naval aviation thought it understood about American aircraft design philosophy. The Hellcat wasn't just better than Japanese fighters. It was built according to entirely different principles that revealed a level of industrial sophistication and tactical foresight that Japanese engineers had consistently underestimated. This is the story of how Japan's most experienced aviation engineers, examining a captured American fighter, discovered they had been fighting a war with one hand tied behind their backs, not because of courage or skill, but because they had never truly understood what they were up against. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The F6F Hellcat was not, by most measures, an elegant aircraft. Standing next to it in Hangar 7, Genda could see this immediately. Where Japanese fighters like the Zero emphasized lightness and maneuverability through careful weight reduction and streamlined design, the Hellcat was blunt, heavy, almost brutish in appearance. Its fuselage was thick and ungainly. The cowling that housed its massive Pratt & Whitney R2800 double wasp engine protruded forward like the snout of some industrial beast. The wings were straight and utilitarian, lacking the graceful elliptical curves of the Zero's wing design. The aircraft weighed 9,238 pounds empty. By comparison, the Mitsubishi A6M50, Japan's frontline fighter, weighed just 4,136 pounds empty. The Hellcat was more than twice as heavy. This fact alone seemed to confirm what Japanese fighter doctrine had emphasized since the 1930s, that maneuverability, achieved through lightweight and low-wing loading, was the paramount quality in a fighter aircraft. The Zero could outturn any American fighter. This had been proven in combat again and again in the war's early years. Yet the Hellcat had a combat record that made such comparisons seem almost meaningless. By March 1945, Hellcats had achieved a kill ratio of approximately 19-1 against Japanese aircraft. 19 Japanese aircraft were destroyed for every Hellcat lost in air combat. The numbers were so lopsided they seemed almost impossible. How could an aircraft that violated every principle of Japanese fighter design be so devastatingly effective? Commander Genda had been asked to answer precisely this question. At 41 years old, he was one of Japan's most experienced naval aviators, though he no longer flew combat missions. He had been Nagumo's air operations officer during the Pearl Harbor attack and had helped plan the operational deployment of the Kido Butai during the war's opening campaigns. Now he worked at Yokosuka, analyzing enemy aircraft, and trying to understand how Japan's early air superiority had evaporated so completely. The team assigned to examine Bureau No. 5, 8312, included 6 engineers, 3 mechanics, and 2 pilots with combat experience against Hellcats. They would spend the next 4 weeks systematically disassembling the aircraft, documenting every component, every system, every design choice. What they discovered would be compiled into a classified report, a report that would never be distributed widely enough to change the course of the war, but which would serve as a kind of epitaph for Japanese naval aviation, an acknowledgement of truths learned far too late. The first day's examination began with an external inspection. The team photographed the aircraft from every angle, measured its dimensions, and documented the arrangement of its armament. 6 Browning ANM-2 50 caliber machine guns, 3 in each wing. The Americans had removed the lightweight 20mm cannons that Japanese fighters relied on, and instead mounted 6 heavy machine guns, each capable of firing 800 rounds per minute. The ammunition capacity was startling. The Hellcat carried 400 rounds per gun, 2,400 rounds total. The Zero carried just 60 rounds for each of its 2 20mm cannons, and between 500 and 700 rounds total for its 2 7.7mm machine guns. The Hellcat could fire continuously for 30 seconds before exhausting its ammunition. In a dogfight, 30 seconds of continuous fire was an eternity. No pilot would ever actually do this, of course, but the sheer ammunition capacity meant that Hellcat pilots could be far less conservative with their fire than Japanese pilots had to be. More revealing was the placement of the guns. All 6 were mounted in the wings, outboard of the propeller arc. This meant that American armament designers had solved the synchronization problem not by firing through the propeller, but by simply avoiding it altogether. The guns converged at a point approximately 1,000 feet ahead of the aircraft. At this convergence point, all 6 guns could concentrate their fire on a single target, creating what American pilots called the Grumman meat grinder, a cone of destruction that could tear apart a Japanese aircraft in a single burst. Japanese fighters, by contrast, mounted their weapons in multiple locations. The Zero had 2 7.7mm guns in the nose, synchronized to fire through the propeller arc, and 2 20mm cannons in the passes, wings. This split configuration meant that Japanese pilots had to think about different weapons with different ballistic properties converging at different ranges. The Hellcat's design was simpler, more brutal, more effective. But it was when the team began examining the cockpit that the first truly unsettling discoveries emerged. The Hellcat's cockpit was spacious by Japanese standards. The seat was thick and comfortable, with a solid armor plate behind it. The armor weighed 42 pounds. 42 pounds of steel, mounted directly behind the pilot's back and head, serving no purpose except to protect the pilot from enemy fire coming from behind. The Zero had no armor plate. Japanese design philosophy held that the weight penalty was unacceptable, that a skilled pilot would not allow an enemy to get into a firing position behind him. If a pilot found himself in such a position, it meant he had already made a tactical error, and no amount of armor would save him. The Hellcat also had self-sealing fuel tanks. The tanks were lined with a rubber compound that, when punctured, would swell and seal the hole, preventing fuel from leaking out and catching fire. This technology added approximately 130 pounds to the aircraft's weight. The Zero's fuel tanks were unprotected. When hit by enemy fire, they ruptured, leaked, and ignited. Japanese pilots called these aircraft flying Zippos when they were being darkly humorous, though most did not joke about it. They simply knew that if their fuel tanks were hit, they would likely burn to death in their cockpits. The instruments in the Hellcat's cockpit were comprehensive and clearly labelled: airspeed indicator, altimeter, artificial horizon, directional gyro, turn and slip indicator, rate of climb indicator, manifold pressure gauge, tachometer, fuel pressure gauge. oil pressure gauge, oil temperature gauge, cylinder head temperature gauge. Radio equipment included both VHF and UHF transceivers. The VHF radio was a standard AN, ARC-5, allowing communication with other aircraft and with carriers. The UHF system was different. It was Lieutenant Takahashi, one of the electronics specialists on the team, who first noticed the small rectangular box mounted under the instrument panel, connected to an antenna that ran along the fuselage spine. The box was labeled IFF, Identification, Friend or Foe. Takahashi had read about such systems in intelligence reports, but this was the first time any member of the team had seen one in person. The IFF transponder was an electronic device that responded to interrogation signals from friendly radar systems. When a radar operator aboard an American ship or at an American airfield pointed his radar at an aircraft, he saw only a blip on his screen. Without additional information, he couldn't tell whether that blip represented a friendly aircraft or an enemy. The IFF transponder solved this problem. When interrogated by the correct radar signal, the transponder would automatically send back a coded response, identifying the aircraft as friendly. This technology had profound implications for air defense and air combat coordination. It meant that American radar operators could immediately distinguish friendly aircraft from enemy aircraft, even at long ranges and in conditions of poor visibility. It meant that American ships could hold their fire until they were certain an incoming aircraft was hostile. It meant that American fighters could be vectored toward enemy formations with precision, while friendly formations could be tracked and managed efficiently. But what made the discovery truly disturbing was not the transponder itself, but what its presence implied about the broader American approach to air warfare. The IFF system was not a weapon. It did not make the Hellcat faster or more maneuverable. It did not increase its firepower. What it did was integrate the Hellcat into a comprehensive system of air defense and air combat coordination that Japanese forces had never fully grasped. The Hellcat was not designed to be a lone samurai in the sky, relying on pilot skill and aircraft performance. It was designed to be a node in a network, a single element in an integrated system of radar detection, fighter direction, and coordinated attack. Japanese naval aviation had always emphasized individual pilot skill and aircraft versus aircraft combat performance. The best pilot in the best performing aircraft would win the dogfight. This was the fundamental assumption underlying Japanese fighter doctrine. The Zero had been designed to create and maintain this kind of superiority, to give Japanese pilots an advantage in one-on-one combat through superior maneuverability. The Americans had rejected this entire framework. They had decided that integrated systems, radar coordination, and mutual support were more important than individual aircraft performance. They had built an aircraft that was heavier, less maneuverable, and more expensive than it needed to be, but which could be integrated into a larger system of coordinated air warfare. And in doing so, they had made individual pilot skill far less important than the ability to fight as part of a coordinated team. This realization was the first crack in Commander Genda's understanding of the air war. But it was only the beginning. Over the following days, as the team continued their examination, more pieces of the puzzle fell into place. Each new discovery revealed not just American technological superiority in a particular component, but a fundamentally different design philosophy, a different way of thinking about air warfare itself. The Pratt & Whitney R2800 engine, once removed from the aircraft and placed on a maintenance stand, was a revelation in its own right. The engine was a two-row, 18-cylinder radial that produced 2,000 horsepower at takeoff power. It weighed 2,360 pounds. The Nakajima Sakai engine that powered the Zero produced 1,130 horsepower and weighed 1,210 pounds. The American engine was almost twice as heavy and produced nearly twice as much power, but the engineers examining the R2000, 800 quickly realized that the raw power output was less significant than the engine's design characteristics. The R-2800 was built to withstand damage and continue operating. Its components were overbuilt, designed with safety margins that Japanese engineers considered wasteful. The crankshaft was forged from a single billet of steel, a manufacturing process that was expensive and time-consuming, but which produced a component of exceptional strength. The cylinders were forged aluminum with steel barrel liners, again expensive, again overbuilt, but almost impossible to damage severely enough to cause immediate engine failure. Japanese engines were built to tighter tolerances, with less redundancy, with more emphasis on weight reduction. This made them more efficient in terms of power-to-weight ratio, but it also meant they were more fragile. A Zero's engine, if damaged in combat, would usually fail quickly. The R-2800 could absorb tremendous punishment and continue running. American pilots routinely returned to their carriers with engines that had taken multiple hits from cannon shells, engines that were still producing enough power to keep the aircraft flying. This difference in design philosophy extended to virtually every component of the Hellcat. The hydraulic system, which operated the landing gear, flaps, and tailhook, had multiple redundancies. If the primary hydraulic system failed, there was a backup. If the backup failed, there was a manual emergency system. The Japanese engineers found this redundancy almost incomprehensible. It added weight, complexity, and cost, but it also meant that Hellcats could sustain damage that would cripple a Japanese aircraft and still return to base. The landing gear itself was a case study in over-engineering. The main gear legs were massive, heavily reinforced, designed to withstand carrier landings that would destroy the landing gear of most Japanese aircraft. The oleo struts had long travel, allowing them to absorb the tremendous shock of a carrier landing. The wheels were large and mounted on strong axles. The entire assembly weighed several hundred pounds more than the landing gear on a Zero. Why build such heavy, overbuilt landing gear? The answer was simple. Because American carriers expected their pilots to make heavy landings, to bring damaged aircraft back aboard, to operate in rough seas and difficult conditions. The landing gear was designed not for the ideal landing, but for the worst-case landing. Japanese carrier aircraft were expected to make perfect landings, and their gear was designed accordingly. If a landing was rough, if the aircraft was damaged, if conditions were poor, the gear might collapse. But that was acceptable because the pilot should have been skilled enough to avoid such situations. Except that in war, situations are often unavoidable. Damage happens, conditions deteriorate, pilots get tired. The American design philosophy acknowledged these realities and designed for them. The Japanese design philosophy treated them as aberrations, failures of pilot skill, and therefore not worthy of engineering accommodation. The radio equipment in the Hellcat revealed yet another dimension of American technological sophistication. The AN ARC-5 VHF radio was standard equipment in virtually all American military aircraft by 1944. It allowed clear, reliable voice communication between aircraft and ground controllers or ships. The radio had a range of approximately 100 miles at altitude. It was crystal controlled, meaning that frequencies could be changed quickly by inserting different crystals, allowing different tactical formations to operate on different frequencies without interference. Japanese naval aircraft in 1945 typically carried much simpler radios, if they carried radios at all. Early war Zeros often had no radio equipment whatsoever, forcing pilots to communicate through hand signals and wing rocking. Later models included basic radios, but these were often unreliable and had limited range. The idea that every fighter aircraft should be in constant radio communication with controllers and with other aircraft was not part of Japanese tactical doctrine. But for the Americans, this constant communication was fundamental to their entire system of fighter direction. Radar operators aboard ships could see enemy formations approaching from dozens of miles away. They could then radio to Hellcat pilots. vectoring them toward the enemy, providing continuous updates on enemy position, altitude, and heading. The Hellcats would arrive at the interception point already positioned for an attack, already coordinated with other friendly aircraft, already aware of the tactical situation. Japanese pilots, by contrast, often stumbled into air battles with limited situational awareness, forced to rely on visual sighting of enemy aircraft and ad hoc coordination through visual signals. The IFF transponder tied all of this together. It allowed the radar operators to track friendly aircraft, to ensure they were vectoring fighters toward enemies rather than toward other friendly formations. It allowed ships to hold their anti-aircraft fire until they were certain a target was hostile. It meant that American aircraft could operate in complex, overlapping patterns without the constant fear of friendly fire. This was the real significance of the IFF system, and this was what Commander Genda and his team were beginning to understand. The Americans had not simply built better aircraft, they had built a better system, an integrated network of radar, radio, fighter direction, and aircraft design that made individual aircraft performance almost secondary to coordination and system-level efficiency, and Japan had never developed such a system. Japanese naval aviation doctrine still emphasized individual pilot skill, aircraft maneuverability, and the decisive engagement between fighters. Japanese pilots were among the most skilled in the world, particularly in the war's early years. But skill alone could not overcome systematic disadvantages in coordination, in situational awareness, in the ability to mass forces at the decisive point. The examination continued. Each day brought new discoveries, new revelations of American design sophistication. The Hellcats' fuel system included multiple tanks with cross-feed capability, allowing pilots to manage fuel distribution and maintain aircraft balance even with battle damage. The oxygen system for high-altitude flight was simple and reliable. The gun sight was a sophisticated reflector design that compensated for bullet drop and target motion. The cockpit canopy was blown plexiglass, providing excellent visibility in all directions. The pilot's seat could be adjusted for height, allowing pilots of different sizes to achieve optimal positioning. Every one of these features added weight. Every one of them made the Hellcat heavier, more expensive, more complex than Japanese design philosophy would consider acceptable. And yet every one of them made the Hellcat more effective in combat, more survivable, more forgiving of pilot error or battle damage. By the end of the second week, the team had disassembled the aircraft almost completely. Components were laid out on tables throughout the hangar, each tagged and documented. The Hellcat had been reduced to its constituent parts, and in that reduction, the magnitude of American industrial and design sophistication had become impossible to ignore. One evening, Commander Genda stood alone in the hangar, looking at the disassembled aircraft. The fuselage sat on jack stands, stripped of its wings and engine. Around it, tables held hundreds of components, each representing some design choice, some of engineering decision, some prioritization of values. He thought about the Zero, about the aircraft he had helped deploy to such devastating effect in 1941 and 1942. The Zero had been a masterpiece of lightweight design, a triumph of engineering elegance. But it had been designed for a short war, for pilots who would achieve quick victories and return to base unscathed. It had been designed for a war that Japan had planned to win quickly, decisively, before American industrial might could be fully mobilized. The Hellcat, by contrast, had been designed for a long war, for attrition, for losses and damage, and the need to keep fighting despite imperfect conditions. It had been designed by a nation that expected to lose aircraft and pilots, and which had therefore built aircraft that could absorb punishment and protect their pilots. It had been designed by a nation with resources so vast that overbuilding, redundancy, and generous safety margins were not luxuries but standard practice. This was the psychological crisis at the heart of what the examination had revealed. It wasn't just that American aircraft were better, It was that they revealed American assumptions about the nature of war itself, assumptions that contradicted everything Japanese military doctrine had emphasized. The Americans assumed long wars, heavy losses, and industrial attrition. They designed their weapons accordingly. The Japanese had assumed quick victories, decisive battles, and the triumph of superior spirit and skill. They had designed their weapons accordingly. And now, in March 1945, with American forces preparing to invade Okinawa, with the home islands under daily air attack, with Japan's carrier fleet destroyed and its Naval Aviation Corps reduced to desperate kamikaze attacks, it was clear which set of assumptions had been correct. The third week of examination focused on the electrical and avionics systems, and it was here that the full scope of American technological integration became undeniable. Lieutenant Takahashi, working with two other electronics specialists, traced every wire, documented every connection, and tested every component that could still function without external power sources. The Hellcats electrical system operated on a 24-volt DC bus, powered by a generator driven by the engine. This was standard for American military aircraft, but the sophistication lay in how the electrical power was distributed and protected. The system included multiple circuit breakers, clearly labeled and accessible to the pilot, allowing him to isolate and reset electrical faults during flight. If one system failed, it could be isolated without bringing down the entire electrical network. Japanese aircraft typically used simpler electrical systems with fewer protective features. If an electrical fault occurred, it often affected multiple systems simultaneously. Pilots had limited ability to troubleshoot or isolate problems in flight. The American approach, once again, assumed that things would go wrong and designed systems that remained functional even under degraded conditions. But the most significant discovery in the electrical system was not any single component, but rather the evidence of how thoroughly electrical power was integrated into the aircraft's operation. The Hellcat used electrical power for gun firing, for the gun sight illumination, for the radio equipment, for the IFF transponder, for cockpit lighting, for wing-fold mechanism on carrier variants, for the hydraulic pump that operated when the engine-driven pump failed. Electricity was not an auxiliary system. It was central to almost every aspect of aircraft operation. This raised an obvious question. What happened if the generator failed or the electrical system was damaged in combat? The answer was found in a storage battery mounted in the fuselage, a heavy lead-acid battery that could provide emergency power for essential systems. The battery was large enough to operate the radio and basic instruments for approximately 30 minutes, long enough for a pilot to reach friendly territory or prepare for a water landing. Again, the design philosophy was clear. Assume things will fail, assume combat damage, assume worst-case scenarios, and design systems that remain functional under these conditions. The weight penalties were substantial, but the operational advantages were even more substantial. The examination of the gun system revealed further sophistication. Each of the 650 caliber machine guns was electrically fired, triggered by a button on the control stick. The guns were synchronized through an electrical sequencer that fired them in a staggered sequence, reducing vibration and mechanical stress. The ammunition feed systems used powered mechanisms to ensure reliable feeding even during high-G maneuvers. The guns themselves were proven designs, the Browning M2, which had been in service since the 1920s and had been refined through decades of use. Japanese aircraft guns were often more advanced in terms of theoretical performance. The Type 99 20mm cannon fired a more powerful projectile than the 50 caliber machine gun, but the Type 99 was less reliable, more prone to jamming, and had a much slower rate of fire. In the time it took a Type 99 to fire 30 rounds, a Browning M2 could fire 100. The American guns were simpler, more reliable, easier to maintain, and fired more rounds. They represented a classic American approach. Use proven technology, build it well, produce it in enormous quantities. As the examination continued, Commander Genda began to formulate a framework for understanding what he was seeing. The Hellcat was not simply a better aircraft. It was an expression of a fundamentally different industrial and military system. Every component, every design choice, every engineering decision reflected assumptions about warfare, industry, and national resources that were alien to Japanese thinking. The Americans assumed they could afford to make their aircraft heavy because they had powerful engines. They could afford powerful engines because they had advanced metallurgy and manufacturing. They could afford advanced manufacturing because they had enormous industrial capacity. They could afford enormous industrial capacity because their homeland was untouchable, thousands of miles from any combat zone, with resources flowing in from secure supply lines. Japan, by contrast, had always operated under resource constraints. Every pound of aluminum, every gallon of fuel, every hour of skilled labor was precious. Japanese engineers had learned to design aircraft that did more with less, that achieved maximum performance with minimum weight, that relied on pilot skill to compensate for material limitations. This had worked brilliantly in the war's early years, when Japanese pilots were veterans and American pilots were novices, when Japanese aircraft could operate from forward bases and American aircraft had to fly long distances from carriers. But as the war progressed, as Japanese veteran pilots were killed and replaced by hastily trained novices, as American industry reached full mobilization and began producing aircraft in quantities that seemed almost incomprehensible, the Japanese approach had collapsed. Skill could not compensate for systematic disadvantages in aircraft survivability, in system integration, in coordinated tactics enabled by technology. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The fourth week of examination shifted focus to documentation and analysis. The team had gathered an enormous amount of technical data, but now they needed to synthesize it into a coherent report that could be distributed to operational units and design bureaus. This task fell primarily to Commander Genda, who spent long hours in his office at Yokosuka, drafting and revising the report that would summarize their findings. The report, when completed, would run to over 200 pages. It would include detailed technical specifications, photographs, engineering drawings, and analytical commentary. But the core findings could be summarized in a few key points, and these points were devastating in their implications. First, American aircraft were designed for system integration rather than individual performance. The presence of IFF transponders, sophisticated radio equipment, and comprehensive instrumentation revealed that American aircraft were conceived as elements in a larger system of radar-directed air defense and coordinated attack. Japanese aircraft, by contrast, were designed as standalone platforms, and Japanese tactics emphasized individual pilot skill rather than system-level coordination. Second, American aircraft were designed for survivability and damage tolerance. Armor plate, self-sealing fuel tanks, redundant systems, and robust construction meant that American aircraft could absorb tremendous punishment and continue operating. Japanese aircraft were fragile by comparison, relying on pilot skill to avoid damage rather than engineering to survive it. Third, American aircraft were designed for industrial mass production and ease of maintenance. Components were standardized, manufacturing tolerances were relaxed compared to Japanese practice, and designs emphasized reliability over theoretical performance. This allowed American industry to produce aircraft in vast quantities while maintaining quality. Fourth, American aircraft design assumed that pilots were valuable assets to be protected and supported. Heavy cockpit armor, comfortable seats, comprehensive instrumentation, and forgiving handling characteristics all reflected a philosophy that treated pilots as expensive, hard-to-replace resources. Japanese design philosophy, by contrast, assumed pilots would compensate for aircraft deficiencies through skill and determination. Each of these findings pointed to the same fundamental conclusion. The United States was fighting a different kind of war than Japan had prepared for. The Americans were fighting an industrial war, a war of attrition, a war of systems and coordination and overwhelming material superiority. Japan was fighting a war of spirit and skill and individual heroism. Both approaches had internal logic, but only one approach was suited to the reality of modern industrial warfare in the mid-20th century. Commander Genda understood, as he compiled his report, that these findings came far too late to change anything. By March 1945, Japan's naval aviation had been effectively destroyed. The carriers that survived the battles of 1944 sat in port without aircraft or trained pilots. The air groups that once dominated the Pacific skies had been reduced to kamikaze units, one-way suicide attackers whose only value lay in their willingness to die. The war was lost, and everyone who was honest with themselves knew it. But the report still needed to be written, not because it would change the outcome, but because the truth needed to be documented. Future Japanese engineers, if there was to be a future for Japanese aviation, needed to understand what had gone wrong, needed to see clearly the mistakes and misconceptions that had led to defeat. As Genda wrote, he found himself returning repeatedly to the IFF transponder. It was a small device, almost incidental compared to engines and guns and fuel systems, but it symbolized everything the examination had revealed. The IFF transponder was worthless in isolation. It only had value as part of a system, a network of radar stations and fighter directors and coordinated tactics. It represented a philosophy that valued integration over individual performance, system-level efficiency over component-level excellence. Japanese military culture had never produced such a philosophy. The emphasis had always been on the individual warrior, the skilled pilot, the decisive personal combat. Technology was meant to serve the warrior, to enhance his capabilities, not to replace his judgment or constrain his actions. The idea of aircraft as nodes in a network, of pilots as operators following vectors from ground controllers, was alien to Japanese tactical thinking, and yet this alien philosophy had proven devastatingly effective. American pilots, many of them with only a few months of training, had achieved kill ratios against Japanese pilots that would have seemed impossible a few years earlier. They had achieved these ratios not through superior individual skill, but through superior system integration. They had been vectored to interception points by radar. They had coordinated their attacks through radio. They had fought in mutually supporting formations, with aircraft covering each other, with damaged aircraft protected by healthy ones. And they had flown aircraft that could survive mistakes and battle damage and continue fighting. The final section of Genda's report dealt with implications and recommendations. This was the most difficult section to write, because the honest implications were so bleak. Japan could not suddenly develop the industrial capacity to match American production. It could not suddenly create an integrated air defense system comparable to what the Americans had built. It could not suddenly retrain its pilots and redesign its aircraft according to American principles. The war would be lost before any of these changes could take effect. But Genda wrote the recommendations anyway, knowing they were for a future that might never come, for a Japan that might not survive the war. He recommended comprehensive reform of aircraft design philosophy, emphasizing survivability and system integration over weight reduction and individual performance. He recommended development of radar and radio networks for coordinated air defense. He recommended changes to pilot training that emphasized formation tactics and coordination over individual dogfighting skill. He recommended studying American industrial methods and adapting them to Japanese conditions. Most importantly, he recommended a fundamental shift in thinking about air warfare itself. The age of the individual pilot as the decisive element in air combat was over, he wrote. Modern air warfare was a competition between integrated systems, and victory would go to the side that could most effectively coordinate its technological, industrial, and human resources into a coherent whole. These words, written in an office at Yokosuka in March 1945, would prove to be among the most accurate assessments of air warfare's future evolution. But they came too late to save Japan's naval aviation, too late to prevent the catastrophe that was about to unfold over Okinawa and the home islands. The completed report was classified top secret and distributed to a limited number of senior officers and aircraft designers. Most of them already understood, in broad terms, what the report contained. They had seen the evidence in combat reports, in loss statistics, in the progressive degradation of Japanese air power. The examination of Bureau No. 58312 had simply confirmed, in meticulous technical detail, what combat experience had already taught. In early April 1945, American forces invaded Okinawa. The Japanese response included massed kamikaze attacks, waves of suicide aircraft crashing into American ships. Over 1,900 kamikaze sorties were flown during the Okinawa campaign. Many were intercepted by Hellcats, vectored to interception points by radar, coordinated through radio, operating as part of the integrated air defense system that the examination of Bureau No. 58312 had revealed in such detail. The Hellcats defending the American fleet around Okinawa had IFF transponders, just like the one Lieutenant Takahashi had examined. Those transponders allowed American radar operators to track every friendly aircraft, to coordinate combat air patrols, to vector interceptors toward incoming raids with precision. The system worked exactly as designed, and the kill ratios against Japanese aircraft remained lopsided until the war's end. Commander Genda survived the war. In the post-war period, he would become one of the architects of Japan's air self-defense force, applying many of the lessons he had learned from examining Bureau No. 58312. The report he wrote in March 1945 would become required reading for post-war Japanese aviation engineers. A case study in how technological and doctrinal assumptions can create vulnerabilities that only become apparent in combat. The F6F Hellcat itself, Bureau No. 58312, was destroyed in an American bombing raid on Yokosuka in July 1945. The hangar where it had been examined took a direct hit from bombs dropped by aircraft, remarkably similar to the one the Japanese engineers had spent a month studying. The irony was not lost on those who survived. The story of Bureau No. 58312 and its examination at Yokosuka is not well known outside specialist circles. It never achieved the fame of other captured equipment analyses, like the German study of the Soviet T-34 or the American examination of the Japanese Zero captured at Akutan. Perhaps this is because it came so late in the war, when the outcome was no longer in doubt. Perhaps it is because the findings were too painful for post-war Japanese historians to dwell on, too revealing of fundamental errors in pre-war military planning. But the story deserves attention because it illustrates something important about the nature of technological competition in warfare. It is not enough to build good individual weapons or to train skilled individual warriors. Modern warfare is fought by systems, by integrated networks of sensors and weapons and communications that must work together as a coherent whole. The side that understands this first, that builds its military power according to systems-level thinking rather than component-level thinking, gains an enormous advantage. The Japanese Navy entered World War II with excellent aircraft and superbly trained pilots. The Zero was genuinely superior to most Allied fighters in 1941 and 1942. Japanese naval aviators had years of combat experience from the war in China. Their tactics were well developed and aggressively offensive. On paper, Japanese naval aviation should have been able to maintain air superiority for years. But Japanese planners had not understood that they were entering an industrial war against an opponent with vastly greater resources. More critically, they had not understood that American military development was moving toward system integration, toward warfare, conducted by coordinated networks rather than by individual platforms. The IFF transponder in Bureau number 58312 was a small symbol of this larger reality. When Lieutenant Takahashi first identified the IFF transponder, he had not immediately grasped its significance. It was just another electronic component, interesting from a technical standpoint but not obviously important. It was only as the team continued their examination, as they documented the radio equipment and the instrumentation and the design choices that prioritized reliability and survivability, that the IFF transponder's true meaning became clear. It was not just a device for identifying friendly aircraft. It was evidence of an entire philosophy of warfare, a philosophy that assumed coordination and integration and system-level thinking. This realization was profound and disturbing because it revealed that Japan had been fighting the wrong kind of war. Japanese doctrine emphasized decisive battle, individual skill, and aggressive offense. These were not foolish principles. They had served Japan well in conflicts against China and Russia in previous decades, but they were not suited to industrial war against an opponent like the United States. The Americans had accepted that war would be long, ugly, and attritional. They had designed their weapons accordingly. They had built aircraft that could take damage and keep flying because they knew aircraft would be damaged. They had installed radios in every aircraft because they understood that coordination was more valuable than individual brilliance. They had developed IFF systems because they knew that friendly fire was a real problem in complex battles with many aircraft operating in proximity. Every one of these design choices reflected realistic assumptions about the nature of modern war. Every one of them accepted imperfections and planned for worst-case scenarios. And every one of them represented thinking that Japanese military culture was difficult or even distasteful. In Japanese military tradition, there was a concept called Yamato Damashi, the Japanese spirit, which emphasized courage, self-sacrifice, and the triumph of will over material circumstances. This concept had deep roots in Japanese culture and had been central to military training for generations. It was not mere propaganda. It reflected genuinely held beliefs about what made warriors effective. But Yamato Damashi could not overcome systematic disadvantages in industrial capacity, system integration, and technological sophistication. Spirit alone could not make a Zero's fuel tanks stop burning when hit. Courage alone could not give Japanese pilots the situational awareness that American pilots gained from radar vectoring. Determination alone could not make the Japanese industry produce aircraft at a rate comparable to American factories. The examination of Bureau number 58312 forced Japanese engineers to confront these realities in the most concrete possible terms. Every component, every system, every design choice in the Hellcat testified to the power of industrial resources applied intelligently according to realistic assumptions about warfare. The Hellcat was not a perfect aircraft. It was not even the most advanced fighter flying in 1945. But it was perfectly suited to its role in the American system of naval air warfare, and that made it devastatingly effective. After the war, many Japanese naval aviators wrote memoirs and participated in interviews about their wartime experiences. Several mentioned the examination of captured American aircraft at Yokosuka, though few discussed it in detail. The dominant tone in these recollections was not bitterness or resentment, but rather a kind of rueful acknowledgement that they had fundamentally misunderstood what they were up against. One former Japanese pilot, interviewed in the 1960s, put it this way: "We thought we were fighting a war between warriors. We, trained to be the best individual pilots, to fly the most maneuverable aircraft, to win through skill and courage. The Americans were fighting a different war entirely. They were fighting an industrial war, a war of systems and numbers and coordination. We never understood this until it was too late." This statement captures the essential lesson of Bureau number 58312's examination. The war in the Pacific was not primarily decided by aircraft performance or pilot skill, though both mattered. It was decided by the ability to integrate technology, industry, and tactics into a coherent system that could sustain itself over years of attritional combat. The United States had this ability. Japan did not. The IFF transponder, in this context, becomes more than just a technical curiosity. It becomes a symbol of different national approaches to warfare. The Americans saw warfare as a problem that could be solved through engineering, through system design, through the application of industrial resources to create integrated networks of mutually supporting capabilities. The Japanese saw warfare as a test of national character, a contest of wills in which courage and skill would triumph over material disadvantages. Both visions had elements of truth. Courage and skill did matter. Japanese pilots performed remarkable feats throughout the war, achieving impossible victories through sheer determination. But in a long war of attrition, courage and skill were not enough. The side with better systems, more resources, and more realistic planning would inevitably prevail. This lesson extended far beyond the specific case of the Hellcat versus the Zero. It shaped post-war thinking about military affairs in profound ways. The development of modern air power, with its emphasis on integrated air defense systems, AWACS aircraft, data links, and networked operations, all flowed from the systems thinking approach that the Hellcat represented. The age of the individual pilot as the decisive factor in air combat truly did end during World War II, just as Commander Genda had written in his report. Today, military aircraft are designed from the outset as parts of larger systems. Stealth fighters like the F-35 are as much about their ability to share information and coordinate with other platforms as they are about their individual performance characteristics. The sensor fusion and data link capabilities that allow modern fighters to operate as parts of networked systems are direct descendants of the basic concepts that the IFF transponder represented in 1945. The Japanese engineers examining Bureau number 58,000, 312 inches, March 1945, could not have foreseen this evolution in detail, but they could see its beginning and could recognize in the Hellcat's design the outline of a future in which warfare would be increasingly dominated by system integration rather than platform performance. Their report, written too late to affect World War II's outcome, became a founding document for post-war Japanese thinking about air power and military technology. The final irony of the Bureau number 58312 story is that the lessons it taught were learned primarily by the defeated, not the victors. American post-war air power doctrine continued to emphasize system integration and networked operations, but this was simply a continuation of existing practice. For the Americans, the approach that had worked in World War II was validated and refined, not revolutionized. For Japan, however, the examination of the Hellcat represented a fundamental break with previous thinking. Post-war Japanese defense forces, when they were eventually permitted to rearm, built their capabilities around principles of system integration, coordination, and realistic assessment of technological and industrial limitations. The lessons Commander Genda extracted from examining Bureau number 58312 became core principles of Japanese defense planning. In this sense, the defeated learned more from their defeat than the victors learned from their victory. The Americans already understood systems-level thinking because they had developed it organically through industrial experience and technological innovation. The Japanese had to learn it through painful defeat, through the examination of enemy equipment that revealed how completely they had misunderstood the nature of modern warfare. Bureau number 58312. That single Hellcat forced down near Iwo Jima and salvaged for examination, thus played a role in history far beyond its service as a combat aircraft. It became a teacher, an artifact that educated its enemies about the principles that had defeated them. The IFF transponder inside it, that small device Lieutenant Takahashi had puzzled over, became a symbol of the gap between two different philosophies of warfare, two different approaches to the application of technology and industry to military ends. The Hellcat did not win the Pacific War by itself. No single weapon system ever does. But aircraft like the Hellcat, designed according to principles of system integration, survivability, and realistic assessment of combat conditions, were essential elements of the American victory. And the examination of Bureau No. 58312 at Yokosuka, conducted too late to change the war's outcome, nevertheless provided invaluable lessons about why that victory had been inevitable from the moment the United States decided to fully mobilize its industrial and technological resources. Commander Genda, writing his report in the spring of 1945, understood that he was documenting not just an aircraft, but a philosophy. The Hellcat represented American thinking about warfare, about technology, about the relationship between individual heroism and systematic coordination. It was a lesson written in aluminum and steel, in electrical circuits and hydraulic systems, in armor plates and self-sealing fuel tanks. The lesson was simple. In modern industrial warfare, system-level thinking defeats component-level thinking, coordination defeats individual brilliance, and realistic planning defeats heroic improvisation. These principles, revealed through the examination of a single captured aircraft, would shape military thinking for decades to come. The story of Bureau No. 58312 thus stands as a kind of epilogue to Japanese naval aviation's tragic arc. From the brilliant victories of 1941 and 1942, through the attrition of 1943 and 1944, to the desperate kamikaze attacks of 1945, Japanese naval aviation followed a trajectory from triumph to catastrophe. And in that catastrophe, in the examination of a captured enemy aircraft, came understanding that arrived too late to matter, but which would resonate through the decades that followed. The IFF Transponder, sitting in its small box under the Hellcat's instrument panel, represented everything Japanese engineers had failed to understand about their enemy. It was not a weapon, it did not directly destroy Japanese aircraft, but it was part of a system, and that system, multiplied across thousands of aircraft and ships and radar stations, had destroyed Japanese naval aviation as surely as any bomb or bullet. This was the final lesson of Bureau No. 58312, that in modern warfare, the invisible system is often more powerful than the visible weapon. The Hellcat's guns could be seen and understood. The IFF transponder, and the vast network of coordination it enabled, was harder to see but far more significant. Japanese engineers, examining the aircraft piece by piece, finally understood this truth. But understanding came at the end, when the war was already lost, when the lessons could only be applied to a future that would be shaped by defeat rather than victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.